Hello, everyone. I will be talking today about disparities in urban heat hazard and exposure. And most of the focus will be on the United States and cities in the United States, but I will also be talking about some work done in the global south. So, urban areas have rapidly expanded in the past few decades. And you can see this here with the overall amount of built up area by country in this animation, as well as how urban areas, individual urban areas, have grown in urban extent over time for various large cities all over the world. This is important because urbanization has impacts on weather and climate. And this is not just because of the increase in urban area, which is the increase in urban extent, but also changes in surface properties due to urbanization, as well as anthropogenic activities in cities, like humans affecting weather and climate through their activities. Overall, urbanization has various different pathways by which it can impact or the climate. This includes localized warming, which is what we call the urban heat island effect, localized drying or the reduction in relative humidity, which we call the urban dry island effect, changes in cloud formation and precipitation, particularly downwind of cities, enhanced air pollution, etc. Of this, the topic I will be talking about, and probably the most common topic in the urban climatology space, is the urban heat island effect. So this is a phenomenon where cities tend to be warmer than their surroundings. And this, of course, leads to higher potential for local heat stress, higher energy use, secondary air pollution, etc. And there are many different factors that lead to the urban heat island. I'm not going to go into all of them, but some of them include like the replacement of natural surfaces and vegetated surfaces with impervious ones, the morphology of urban areas and buildings, which tend to trap long wave radiation, changes in evaporative cooling due to, again, the replacement of vegetation with impervious surfaces, anthropogenic activities, as well as other impacts such as the aerosols, which can also sometimes trap long wave radiation near to the surface. And the urban heat island is important because as the planet grows more urban as well as warms, you will have more and more people moving to urban environments, which means that in addition to the overall warming, you will have an additional warming due to urban heat islands. So this will have long-term health consequences as I said, there is a lot more rural to urban population migration associated with urban expansion. Here's an example of some work we did in cities in California, where we had estimates of heat-related emergency room visits for at the zip code level, and this is over a 10-year period. And what we found was that this was significantly associated with the spatial variability of the land surface temperature and the surface urban heat island in many of these larger cities. And we also were able to estimate how potential urban afforestation, if we kind of replaced all the pervious land with vegetation, how that would reduce this heat-related emergency room visit. And we found that this would reduce this by around 3,705 over this period for the cities for which we had statistically significant relationships. But that's probably the only public health-related thing I'm going to be talking about, but most of my work is focused on the environmental hazard and exposure side. So in addition to the overall urban heat island effect, urban areas also tend to be very heterogeneous. So you can see examples here for New York City, where you have very different mixture of building types, building materials, as well as combinations of vegetation and buildings. And what this means is that the urban heat island effect also tends to be very spatially variable. Here's an example again for the New York urban cluster, where you can see the surface urban heat island, which is the urban heat island as seen from satellite derived land surface temperature. And you can see large variabilities going from less than 1.5 degrees Celsius to over 7.5 degrees Celsius. The way this spatial variability is distributed within cities also has impacts on or different impacts on different population groups. In the US particularly, we find that in most cities, the urban heat island, as well as temperature in general, tends to be higher in poorer neighborhoods and neighborhoods with more non-white populations. So here's an example from the 175 largest cities in the US, where we find that in over 90% of the cases, you have heat-related disparities by race and income. Um, Here is an example of a web application which I developed several years back, which shows the data for the surface urban heat island intensity by census tracts, as well as the US census data, kind of side by side. And what you can do is kind of explore the different urban heat island estimates for daytime, nighttime, summer, winter, etc., as well as several of the relevant census information like income, proportion of population of different races and ethnicities, etc. And you can also click on these and find out what is the relationship between the summer daytime urban heat island and income. That's kind of showing up in the plot right here. And you can kind of see, like, as I choose like a different city that is going to get updated, but you generally see again mostly negative associations, which is as the income increases within the city, the urban heat island decreases.
Excuse me, TC.
Yeah.
So, because of the notion of heat island is so critical to what you are saying, could you clarify exactly why do you call it an island?
Yeah, I mean, basically, the urban areas are islands in the middle of the rural landscape. So when we define the urban heat island, we normally define it as the temperature difference between the urban area and the surrounding rural area. That's why it's called an island, and that's how it kind of came about the terminology.
So, in places where there are no tall buildings, how
Mhm.
how would this definition translate?
So you can still, so in that, so the urban heat island definition is kind of more of a legacy definition than what's kind of used in practice. So if you have no tall buildings, you might still have warmer temperatures than, say, the rural area outside the city, but the magnitude might be not as different. So what we can also call it is some people also call it an urban temperature anomaly, which allows you to no longer use the island definition. But traditionally, we have used urban heat island as the term, and it's kind of stuck in the literature. I hope that makes sense.
Okay, thank you.
So, in addition to the disparities in temperature and urban heat islands, you have parallel disparities in vegetation. At least that's what we see across U.S. cities. Here's an example for um, urban urbanized areas in the U.S. that I used in this analysis, and then I'm looking at the uh, basically the summary of the slopes of regressions of various vegetation estimates. So tree fraction, grass fraction, tree plus grass fraction, non-tree vegetation percentage. This is from a different satellite. Tree percentage from this is a different satellite from than these three. And then a vegetation index, which is not exactly tree percentage, but gives a overall estimate of the greening or photosynthetic activity of the surface that the satellite is viewing. But what we find in all cases is that the median, as well as most of the slopes, are positive. That means as the income increases, the amount of vegetation in that neighborhood increases. So, and this vegetation disparity is the primary reason for the disparities in heat that we saw earlier on. Now, one thing to note about a lot of the analysis I showed earlier was using satellite derived land surface temperature. And the reason we have used satellite derived land surface temperature is because it's globally available, it's spatially continuous, and it's generally much easier to process versus ground based sensors of or sensor estimates of air temperature, which is what is more relevant to human exposure. However, it's very rare to get urban air temperature measurements because the standard like siting criteria for weather stations does not really include urban areas, especially like impervious surfaces in urban areas. So there are various differences between what we get from satellites, the land surface temperature, and what we would get from 2 meter air temperature estimates from weather stations. So as I already mentioned, the advantages for satellites are that these are global scale, they are spatially continuous, and generally are easier to work with because of widespread data availability. But the disadvantages are that during cloudy conditions, you don't get estimates of land surface temperature. There are also view angle differences between satellites, which lead to somewhat different estimates of the land surface temperature, especially when you have a lot of rooftops blocking the view of the sensor. And most importantly, it is not equivalent to the human perception of the environment, because you would have to touch the warm surface without, say, a shoe on, or kind of with your bare skin, to be able to experience the temperature that we are getting from land surface temperature. So this is why we did another analysis to try to understand whether the disparities we find for land surface temperature are consistently seen for air temperature, as well as for other estimates of heat stress that are more relevant to human physiology. So for this, we ran a single layer urban canopy model over the continental US at 1 kilometer resolution. This was done at the daily level using 30 for over 30 years, but I'm going to be mostly showing the results for the last 5 years. And then we took the model outputs, and from the model outputs, we aggregated them by census tract polygons, and then aggregated satellite-derived land surface temperature in parallel to do a comparison. We also aggregated them by redlining zones, and basically the redlining grades, and I'm going to be giving some examples of those results as well. In addition to air temperature and the modeled skin temperature, we also estimated two moist heat stress indices. The first being the heat index, which is used by the National Weather Service, the US National Weather Service, and the humidex, which is used in Canada for estimating physiologically relevant heat stress. So here I'm showing the sensitivity of the heat index to income. So basically what I'm showing is the slope of those regressions of the heat index versus income. Essentially, how much does heat index change as you increase income by $10,000? And what you see in all cases, well, most cases, is that you have negative values, which is consistent with what we found for land surface temperature, that as the income increases, the air temperature as well as the heat stress goes down. So we do find pervasive disparities in moist heat stress in US cities. Another very interesting result that we found was that the degree of disparity in heat stress was strongly associated with the degree of racial segregation. So here, racial segregation is defined by the dissimilarity index, which shows the amount of segregation between white and non-white populations within an urban area. And we estimate the magnitude of disparity in heat using the environmental concentration index. Basically, this allows us to remove the unit from the disparity estimate, and map it between -1 and +1. But what we find is a pretty strong negative association, which generally shows us that the more segregated a city is in the US, the higher the magnitude of disparity in heat stress within that city. However, and this is going back to a criticism of the land surface temperature, which I mentioned earlier, is that when you look at the magnitude of the disparity, this is given, of course, by the slope of the regression. You can see that for, say, land surface temperature, the magnitude, the median slope is 0.9. For air temperature, this goes down to like 0.6. For heat index and humidex, it goes down further to -0.55. And part of this difference between the heat stress index and air temperature is because the richer neighborhoods also tend to have a higher relative humidity. And higher relative humidity, all else being the same, would lead to more heat stress. So overall, if you use land surface temperature, you are generally getting the right direction of the disparity, but you are generally significantly overestimating the magnitude of the effect. Now, one thing to note here is that there is something else here called skin temperature. And the reason I bring that is because these are model simulations. Modeled skin temperature is somewhat different from satellite-derived land surface temperature. When satellites look down at the city, it's seeing whatever is in the field of view. So this could be part of the roof, half of, say, a building wall, part of the road, etc. While what satellites give us when it comes to skin temperature is an aggregated value of the radiative temperature or whatever the model defines as urban. So it would include like all of these urban surfaces in its estimate of skin temperature. So there are some differences fundamentally between these two variables, which also affects the difference in sensitivity we see here.
So the skin temperature, um, it's it's not actually measured, or how is the how?
These are all, so these variables are all modeled because we are
Okay.
running uncoupled 1 kilometer model over the corners. That is the only way we can actually get air temperature and humidity at the scales that we want. While land surface temperature is actually measured or rather retrieved using an algorithm based
Mhm.
on measured thermal radiation from the surface. And the thermal radiation is not coming from all surfaces equally. It is coming from different parts of this pixel based on the angle at which the satellite is looking down at the surface.
So let me, and again, this is fascinating. I'm asking out of ignorance. So is this estimated with actually cubes, or with a human type of typology? Because we know the head, it has a relative importance in terms of heat.
Mhm.
And is this account for the sweating?
So land surface temperature does not account for any of that. It's
Yes,
just
yes.
the, yeah. If
The
you,
heat, the skin temperature.
the skin temperature is the skin temperature of not the human skin. It's the temperature of the skin of the surface in the model. So
Oh, I
yeah,
thought it was the human
no,
skin.
no. Yeah, we use some similar terminologies. It's the skin of the Earth's surface, essentially.
Oh, I see. Because I thought that skin temperature is a really nice, I
It would
mean,
be great to be able to get skin temperature, yeah, from the models, but these models are not for humans.
huh, but maybe, it could be somehow extended.
It's possible, yeah.
I bet that will be related to, I mean, they should be
So I
related.
know, so that's how a lot of the human physiological models come about, that they will look at the ambient temperature and then assume general, um, base metabolic rates of humans, as well as energy expenditure, as well as, what temperature you would have to maintain the um, skin at to allow regular thermoregulation, and based on that they will find certain critical ambient temperatures under which the human body can no longer survive. So that's what they do in those models, but those are somewhat simplistic in terms of choosing the factors for humans themselves, because humans are very varied, right? So they will have very large variability in um, base metabolic rate, or like energy requirement, or even like activity level, which has an impact on the energy balance of the body. But that is done in not these kinds of models, but somewhat different physiological models
Oh,
used in,
okay.
yeah.
So when you refer to skin, it's this the skin of the environmental temperature.
Yep.
So it means that it it contains different variables. It's derived using different variables. Is that?
That's right. I mean, yeah, different variables, different surfaces. So the skin temperature for a car, like if you keep your car parked outside, it's gonna heat up. When you touch the car, that's the skin temperature of the car. But when we're talking about a 1 kilometer grid, there are multiple different things in the grid, including say uh, grass, trees, buildings, building roofs, building walls, roads. All of that is kind of combined when you get the average value of the 1 kilometer grid.
Okay. So what with these values that you have here would say higher for richer populations and higher for poorer populations. Are all these part of the skin?
No, so this is only skin temperature. This one is air temperature. This is
Okay.
relative humidity. This is heat index, and this is humidex. So air
Okay.
temperature is for 2 meter air temperature. So that is somewhat representative of what you might feel when you're outside. So is relative humidity, heat index, and humidex. The skin temperature is only used here for the comparison with land surface temperature, because these two variables are both based on radiative temperature of the surface, but of course of very different surfaces. One is a observed surface as seen by satellites, and the other is a modeled surface as represented in this urban canopy model. But the
Mhm.
other variables are all relevant to essentially 2 meter ambient conditions.
Okay, okay. So, so in this in this graph that you have here with the differences between richer and poorer populations, then it's definitely the sensitivity it's lower in the sense that they feel more hot, more heat in the poorer populations. Is that the
So
interpretation?
yeah, that is consistent. And in most cases, you do see higher temperatures in poorer populations. That's why the sensitivities are negative. So as the income goes up, the temperature decreases. But the question is the magnitude of that disparity, and the magnitude is given by those slopes, right? So the slopes are giving you what is the unit change in one variable as a function of the unit change in the other variable.
What
And
is
what we find
RH?
is, sorry,
What is RH?
a relative humidity.
Okay, and why is such a different variable from the others?
Because relative humidity is going to be higher in suburbs and in more vegetated areas, because vegetation locally increases humidity. So in the US, a lot of the richer populations live in the suburbs and also in more vegetated areas. So there, the relative humidity is going to be higher. So you see the opposite effect for relative humidity, in that richer populations have higher relative humidity than poorer populations.
Awesome. Thank you so much.
So, in addition to looking at the overall urban areas, we also looked at this and did this analysis by different redlining grades. So, redlining was this historical practice of defining neighborhoods based on their existing racial as well as um uh, class makeup, and also giving different mortgage rates based on that. And what that essentially led to is certain neighborhoods were essentially disenfranchised from owning property over generations. And basically, it goes from A being the best graded neighborhood to B being still desirable, C being definitely declining, and D being hazardous, which is what we normally call the red line neighborhoods. So we looked at the temperature anomalies for each of these redlining grades for roughly 190 cities for which we have data. And the anomalies were essentially calculated as the temperature of that grade minus the average temperature of all of the grades in the city. And what we find generally is that even in the present day, the best graded neighborhoods historically, this was like, in the 1930s, still show the lowest temperature. Then are the B grades, then the C grade, and the D grade. So essentially, the red line neighborhoods still show the highest temperature within a city. But again, we are showing different variables here to show that the magnitude of the effect is different for skin temperature, air temperature, heat index, and humidex. So for humidex, we generally see the least difference between the grades, while for skin temperature, we see the greatest difference. Now, all of this analysis was done using an uncoupled model, which has certain uncertainties, particularly related to the ability to capture advection. So, in a separate study, we wanted to use a coupled model to try to understand the relationship between these different variables and how they relate to disparities more clearly. So here, what we do is we run an ensemble, and an ensemble is essentially we run the same model with 5 different initial conditions, because each model run is going to have a slightly different climate realization. So you want to see that if the results are consistent across these different simulations or not. So we run this very kind of the state of the art model called weather research and forecasting with a building energy parameterization and the building effects model. and then we sorry building energy model, and then we run over the Great Lakes region with a focus on the Chicago area and the 77 community areas within Chicago. We choose the community areas because there's a lot of socioeconomic information available for the area, and we can also look at disparities by these community areas. So here I'm showing the results for not just the different ensembles which are given by this error bar, but also different ways of running the model. This includes different ways of representing the boundary layer, different land models, and different way of configuring the model to go from coarser resolution to finer resolution. We are also considering not just skin temperature and air temperature, but also wet bulb globe temperature. The previous variables we used were heat index and humidex. Heat index and humidex are only a function of temperature and humidity, and they are only defined as a physiologically relevant heat stress metric for shaded conditions. On the other hand, wet bulb globe temperature includes the impact of radiation and wind, which are both very important for human heat loading. Radiation, because it's directly affecting the amount of heat absorbed by the human body, and wind, because it is affecting how the sweat is evaporated from the body, and thus, like, overall, the thermoregulation of the human body. But what is interesting here is that for daytime, we find consistent results that the magnitude will be different. That's fine because these are very different model simulations with different assumptions about the various components of the Earth system. But what is consistent is that in all cases, you do see a disparity by income. So as the income increases, your skin temperature, air temperature, wet bulb globe temperature all go down. However, again, the disparities magnitude is different for skin temperature, air temperature, and wet bulb globe temperature. And this shows a much more clearer, you know, estimate of what I was showing earlier, where because I was aggregating all of those slopes into one chart, so it was not as easy to see. But here you can see that what's happening with skin temperature is that skin temperature tends to be much higher in magnitude than the others, and also has a lot more variability with income than the others. Then comes air temperature, and then finally wet bulb globe temperature.
What is wet bulb?
So wet bulb globe temperature is essentially a temperature. It comes from three different measurements. So it includes the temperature of the dry bulb temperature, which is normal 2 meter air temperature. Then wet bulb temperature. Wet bulb temperature is essentially an estimate of the moisture holding capacity of an air parcel. So it includes the impact of temperature and humidity. And then finally, you have the black globe temperature, which is basically shows the temperature in direct sunlight. So all of these three are combined to give something called the wet bulb globe temperature. The variable came out of a lot of work in it was used a lot in like the military operations for military training. So basically, it would when wet bulb globe temperature would go about 90 degree, they would have a black flag event and essentially stop or reduce training volume because it is related to heat exhaustion. More recently, wet bulb globe temperature is the ISO standard for occupational heat stress, and it has more recently been incorporated into the dashboard created by the National Weather Service. So originally they used to only use heat index, but now they also produce maps of wet bulb globe temperature because it is more relevant for looking at outdoor heat hazard um, in kind of non-shaded conditions.
Okay, and when thank you for that explanation. We clarified a lot. So when we look at this graph, I see temperature very high, of course. Uh,
Mhm.
so does that mean that these estimations, um, like what about seasonal changes?
So this is only for summer season.
Okay.
Yeah. All right. So based on these different, mainly these two studies, what we find is that within U.S. cities, this is how the environmental variables and the socioeconomic variables generally vary. So you have surface temperature varying the most, followed by air temperature, and then heat stress. And part of the reason heat stress varies the least is because relative humidity shows the opposite variability, where you have higher relative humidity as you move away from the city and lower relative humidity in the middle of the city. And that's what we call the urban dry island. On the other hand, populations in the US are generally distributed such that richer and predominantly white residents live in the suburbs, while poorer and predominantly non white residents live in the urban core. This is not true everywhere. There are exceptions to the rule, but this is the general distribution of population within cities. But what we find is that the surface temperature from satellites does generally give you the right direction of disparity, but using it to quantify the magnitude of the disparity is not correct, because you're going to generally overestimate the disparity. So especially when we're talking about public health impacts, which does require some of the information about actual magnitude of the effect to get effect sizes on, say, health outcomes. Now, a lot of what we focused on was on moist heat stress and the wet bulb globe temperature, which in theory does have the impact of radiation. But because those models are being run at something like 4 kilometer resolution, you cannot really go down to the pedestrian scales, because when you're at the pedestrian scale, you have impacts on nearby buildings or nearby tree cover, which cannot be resolved at 4 kilometer resolution. So this brings us to some other work we have done on hyperlocal heat stress estimates using what we call microscale models. So these give you estimates at 1 meter resolution, allowing us to kind of separate out the heat stress over streets uh, and like within the urban road networks. And there's like a lot of details here, but what is interesting here is looking at these two maps. This is for Philadelphia. And what you can see is that even higher resolution satellite data, this is 30-meter, well, downscale 30-meter data from Landsat. And this is does not give you enough variability compared to the real variability we see from the microclimate modeling. So here you can kind of see how the mean radiant temperature varies significantly at the meter scale. So like if you're like near a building, you are shaded from the sunlight, which means that you have much lower mean radiant temperature. And this none of this is really resolved in some of our coarser simulations. And more recently, we have estimated these 1 meter resolution mean radiant temperature as well as universal thermal climate index, which is another metric used for getting physiologically relevant estimates of heat loading for various US cities, various large, mostly large US cities. And we have also looked at what this means for disparities in pedestrian scale heat loading. And in most cases, our results are consistent. We still find that there is a negative association between income and the UTCI, the Universal Thermal Climate Index, in most of these cities, which means as the income goes up, the UTCI decreases. So this is consistent now across various different variables that we have considered. Now, one thing I always like think about when I do these kinds of analysis, and this has been pretty standard in the literature, is that we always assume that the where people are according to the census data are where people are getting exposed to heat, and that's not necessarily true, because people don't spend all of their time at home. They travel, they go to work, and they go to work at different hours, peak hours usually for heat loading. So there's been some work on this, and it's much harder to do this kind of work using the data we have available, because mobility data is very hard to get. It's usually proprietary, or you will have to buy it from, say, cell phone providers or something like that. But there has been some work on this, and what they have done is they have actually managed to find different typologies of heat exposure based on where people are traveling to during the hottest time of the day. So they have define these things called like heat escalates, heat escapes, and heat traps. There are uncertainties in these estimates because a lot of the mobility data that they use were from February of 2020, like during the COVID lockdowns, which means that they're not really representative of the typical year or the typical summer period. But it's still a very interesting, I think, framing, and gives us more useful information about heat exposure versus just heat hazard. Now, one thing to note about a lot of the analysis I showed was that it's mostly focused on the US, and I have done a lot of my work in for US cities in the last few years. However, one of the older studies that we did, we looked at 23 global cities, and what we found was that in 67% of the cities, we found a disparity by income, as in a higher income neighborhoods within a city have lower temperature. However, the way these cities were chosen was not systematic. It was just based on the number of data points we had for various large cities. And it was very biased towards US cities as well, or cities at least which are similar in structure to US cities, such as cities in Canada. Um, but there were exceptions to the rule for, say, here we find uh, positive associations between income and heat for instance, Sao Paulo or Beijing, which was an interesting thing and an exception that we did not explore in most of the US based analysis. So, more recently, I have started looking at what the disparities in urban heat hazard might be for cities in the global south. One issue with doing this kind of analysis is that it is very difficult to get high resolution income data within cities in the global south, because normally the data are not released or even ca- even calibrated or estimated at the within city administrative level. So instead, I use this data called the relative wealth index, which is available for the entire global south essentially at 2.4 kilometer resolution, and it's based on survey data as well as information from Facebook. So it's released by Meta. And here's an example of the relative wealth index for Calcutta in India, which is my hometown. And you can generally see is that higher wealth index in kind of the middle of the city and lower wealth index as you kind of move away from the city. So in this analysis, what we did was we looked at around 400 urban clusters globally and estimated the both the heat hazard as well as the relative wealth index distribution within these cities and how they co-vary. And we divided these clusters into these six different regions as defined by the World Bank, including East Asia and Pacific, Sub-Saharan Africa, South Asia, Latin America and Caribbean, Middle East and North America, and Europe and Central Asia. So these plots are essentially parallels to the plots I showed earlier for the for the US cities. The only interesting difference here is you can see that the median slopes are mostly positive, which means that there is higher heat hazard in richer neighborhoods and less heat hazard in poorer neighborhoods in most of these cities. So this is seen when we divide by region, the only exception being for Middle East and North Africa. It's also seen for various estimates of heat. This includes annual air temperature, maximum air temperature, annual minimum air temperature, annual daytime land surface temperature, annual nighttime land surface temperature, and all of its summer versions. So in all of these cases, you see generally pro-poor distribution of heat hazard, while in the US, you are seeing pro-wealthy distributions. So why is this happening? So going back to our distribution of relative wealth index for Calcutta, I'm showing the air temperature beside it. And what you can see here is that the air temperature is highest in the middle of the city. And this is expected. This is expected from most cities. The urban core tends to be the warmest, while the urban temperature reduces as you move towards the suburb. What is what is different from US cities is that in the US, I talked earlier about how the richer populations are moving to the suburbs because that has been the cultural norm for decades. But in cities in the global south, that's not the norm. Richest people generally live in the middle of the city. And this is interesting because that kind of describes why we see the opposite uh, direction of the disparity in for cities in the global south. Here's an example of an app which I also made using this data set, which allows you to explore this data. Like this includes, of course, the air temperature, I think the maximum air temperature, but also other variables. as well as the relative wealth index. And you can generally see here, example, you have a positive association between the maximum air temperature and the relative wealth index, which is different from what we were seeing earlier for cities in the global, sorry, US. For Mexico City, you don't see as much of a variability at all. But something to note is that a lot of the population distributions in North America have been influenced by what happens in the US, including a lot of the distributions in Canada, for instance. Um, all right. So so why so that just goes into like the hazard, right? So exposure would require us to also look at how many people are being exposed to this hazard. So here what we do is we looked at the scaled population weighted Tmax and the relative wealth index deciles within cities. And what we find is that if you even if you consider exposure as you move to the warmest parts of the cities, you actually see more populations, which means if you think about the overall population being exposed to hazard, it is higher for the higher income populations. So why is this happening? And I already mentioned this a little when I talked about the distribution for Calcutta, but we did this for all of the cities in the global south and all cities in the United States. What we did was we estimated the scaled distance uh, from of each neighborhood or each relative wealth index grid from the centroid of the city, and we did the same thing for the scaled maximum air temperature. So what you find for the global south is that both of them follow very similar trajectories. So as you move away from the city, you have a slight increase in relative wealth index, so the income, and you have a slight increase in the maximum air temperature. So somewhere near the urban core is where the richest population live, which is also where you will have the highest temperature. On the other hand, for the US, it is completely opposite. You still have highest temperature nearer to the urban core, but and then of course it reduces rapidly as you move to the suburbs, while for income you have a dip in the income nearer to the urban core, and then the income rapidly increases as you move away from the city. And of course this is consistent with what I mentioned earlier about how income is distributed within US cities. So this difference is essentially what is causing the you know the distributions in the global south to be very different from the distributions in the global, well, the US particularly. And I think this result is important because there is a general tendency of taking US specific information and thinking they are generalizable to everything. And that's not necessarily true. And also, that's relevant for policy decisions. You, maybe adding more vegetation to the middle of the city is relevant for US context, but that's not relevant for uh, equitable heat mitigation strategies in the global south. So we have to have better data to be able to do that. And showing that the global south is different from the US, I think is very important for starting that conversation.
Is
With
it?
Yeah.
Let me ask you about this difference. So interesting. I'm wondering about the difference in architecture, vernacular architecture. So in Africa, in so many places, you don't have air conditioning, and
Mhm.
and you yes you are exposed to nature, but it doesn't feel as hot as in this city that are just ready for air conditioning. I don't know.
So I think.
The architecture, vernacular, that is not
Mhm.
just a catalog where you pick your home, but the way that even the shape of the windows, the size of the windows, having real windows, not just glass walls.
Yeah, glass is going to turn your house into a greenhouse. So, I think so. The two things I focused on was the exposure piece and primarily the hazard piece and the exposure piece. The other part that's very relevant for overall heat risk is vulnerability. And that is something where I think data is even more scarce. So, one of them is, of course, air conditioning penetration. Like in the US, air conditioning is a lot more standard than in most developing countries where air conditioning is only becoming available more recently. So even if, say, in the global south you have higher ambient temperature in richer neighborhoods, that matters little if your richer people have air conditioning, or if they're just taking air conditioned cars everywhere. So I think that's where I think it's important to understand like what policy decisions to make for which population and what works, because reducing ambient temperature may not be the biggest most optimum strategy when your temperature is above 45 degree, because there are limits to how much ambient temperature you can actually reduce even with something like, say, greening, while providing the ability to cool down through air conditioning, through and that could be through like government incentives, may have a much bigger effect on reducing heat related illnesses. So I think that's part of it, and the other issue is that there is a lot of housing that's not permanent in the global south, which have very different response to the same ambient conditions. So if you have like aluminum rooftops, that heats up much more than a lot of regular concrete structures, and a lot of these are in like slums, especially in India, and there's like favelas as well, right? So they will have a very different response to the same ambient conditions, and they of course predominantly impact vulnerable communities and lower population urban residents. So but I think the reason for doing this kind of comparison is to talk about those other aspects being more important, particularly vulnerability and potentially exposure, than the hazard piece itself, because at least in the climate space, urban climate space, or climate in general, our entire focus and our expertise is really understanding and trying to model the hazard. We don't really have enough data or expertise to think about those vulnerability aspect, which requires a lot more understanding about the social structure or human physiology, and just population like demographics in general. So I think that's where like the difference in the approach of different fields come into view, and like the need for more integrated assessments of these issues. Yeah,
Wonderful. Thank you so much.
yeah. So that's all I have. Like I want to thank a lot of people who have contributed to many of these different papers. And if you have any questions, you can reach out to me on my email. I'm also here, I think, for the next half an hour-ish. There's also a list of papers that I uh, kind of tried to summarize the results from. So you can also check out those papers for more information about the work or some of the details on the methodology.
Well, this is amazing to see. This is very, very interesting. And I think you have here a new data set that can be used as a covariate and inserted with multiple factors that we are analyzing here. It would be interesting to know if you have the data from this area of South Texas. Is this area also available?
Yes, it should be all, if it's defined as a census designated urban area or urbanized area, it should be available. And it's very easy to actually estimate these now, just because of all of the availability of global gridded data sets. So uh, it should be pretty simple to get the information. I also have I got a recent NIH. I actually got a proposal funded through the GECC, so like the pilot project to create like Zicta level estimates of various heat stress indices and temperature estimates, as well as vegetation estimates for the US and the world. So that I'm hoping is going to be, we haven't received the funding at our institution yet, but once we get that, I'm really hoping to be able to like develop that data set and release it for broader use in the public health community.
Very, very nice. Well, I would like to open the floor for our audience to have any questions. You have any questions or comments,
I
Dalia?
see Dalia.
Hi. I really enjoyed your talk. I will be honest with you. I'm a philosopher and most of like things about numbers go right over my head. However, I could see, I took pictures of certain models that I saw there, and I guess what I'm thinking about are the more practical aspects, and I'm not sure how involved you are in that. I see that you just said that you would be able to release all this really good information, right, to different groups of people who are doing different kinds of things. But I'm wondering, the laboratory that you work for, do they have partners with different city planning or
So
urban
we
planning?
don't normally directly do policy, like but I have worked with the city of Olympia in Washington. We did some work setting up sensors, and the information from the sensors were used to try to prioritize their land rezoning plans. So
Mm-hmm.
I've done some work, and I'm doing some work with the city of Lowell on a different project, trying to understand energy transition scenarios and how they would be relevant for future warming, for extreme heat, and also extreme like cold snap events, because this is up in Massachusetts. So
Right.
I do work with cities, but it's still from a more academic sense than
Yeah.
directly like
Uh,
informing,
because it
directly.
seems to me that there's just so much that would be useful to people. So that's one thing that was going through my head. The other thing I found interesting, and it's probably way off topic, but I was very curious about you referring to the global south. Uh, I guess I'm thinking about it in terms of the way the globe works, right? You've got this equator, and then you have
It's not.
poles. So I'm very intrigued because I've never heard anybody say the global south, and I mean it's a very intriguing idea. So I imagine that is something that you're sort of like you take in, you don't even think about it anymore.
So I haven't done much. So I think that's a very common terminology, at least for people doing climate work. It's I know a lot of people have problems with the term global south because it's not really, firstly, not in the south. It's more like lower and middle income countries. But then of course Australia is not in it, Singapore is not in it. So what does it represent? But it does have like kind of a historical definition, just coming from like
Yeah.
contrasting with what's happening in like Europe and North America essentially. But I agree. I have had like, I mean, I know people who are not like, don't like the term global south, but it's more of, it's used so commonly that it's easier to
Oh, sure.
call it
Yeah.
that than say lower and middle income countries,
Well,
which is
because
essentially.
I've just been talking to some people, I guess it was 2 weeks ago, talking about the Peter projection, which is another version of how to set up a map, right? Where
Mhm.
the longitude and latitudes are much more accessible and equal in a
Mhm.
way that don't because the one that we use now it it has a false picture of how big
Yes. It,
the
it, it,
countries
it it
are.
makes like mid latitude and up larger than they actually are. Yeah.
Yes. And
They
I
make
mean,
tropical countries relatively look smaller, but yeah.
and so I think that has some relevance with regard to why it is we have so much information about the United States, because according to the map, we're just this big ass
Yeah.
country, right? And when you put it up against like South America or the Indian continent,
Mhm.
that it's nothing. It's
Right.
tiny. So I'm hoping at some point that there might be some discussion of how we might find a way to get rid of that disparity of information, because I think it's incredibly useful. Like I said, numbers don't speak to me as much as how it is you describe these things. So
Right.
you did a great job, and I really appreciated
I
it.
think that's part of the reason I wanted to kind of look beyond the US, because when I came to the US, I was actually surprised by some of the distributions of heat we were seeing, because that's not consistent with what I felt when I was growing up in the city. Because I grew up in a big city, I knew like the richest people were in the middle of the city, and in the US, it's completely different.
Yeah.
So, and it became obvious to me that when people were taking these US level analysis and then making very broad statements about how cities are everywhere, which is not true. At least that's not true from my expertise. So I had went back and did the analysis, and I found it was opposite. And that was, I think that's important for the community to know, not to consider the US to be the norm, because it's
Yes.
very.
That's why it's so important to have people that look like us doing this kind of work, because we provide a different perspective. Thank you very much. I really appreciate
Thank
it.
you.
There any other question here? I have more questions, of course. Something that is also interesting, I saw very, very interesting your comparisons, is that how much of those metrics on the heat map were coming also from pollution, because some areas that are more urban, they also have more cars, more gases, more tail gases coming from the cars, and of course more concentration of the population that makes more probably more frequent or higher that those temperatures. How much do you think is part of this, or just
So,
the concentration, also how concentrated are the buildings, one to the
right. So
so
there are two aspects of this. So first, like the activity, like cars and vehicular emissions, or even say activities in factories or through humans, that does add to the urban heat, and that's what we call anthropogenic heat flux. It tends to not be a big component except at nighttime, and also for specific cities like Tokyo, for instance, has pretty large contributions from anthropogenic heat flux. It's not a huge amount in less kind of densely packed urban areas. The other aspect is pollution itself, like air pollution. So if you have a lot of air pollution in a city, it actually tends to reduce temperature because it actually blocks the sunlight from reaching the surface. So in a lot of very polluted cities in India, for instance, India, Pakistan, China, the air pollution essentially reduces the amount of radiation reaching the surface, and essentially also reduces the urban heat island effect. There's a whole other concept called urban pollution island and how it relates to urban heat islands. So there are two aspects of it. One is like the actual activity happening due to humans and vehicular emissions and so whatnot, and how that adds to the urban energy budget. And the second is how the amount of energy that reaches the surfaces might be reduced by the urban air pollution. But generally, of course, urban air pollution tends to have much worse impacts on health than the changes in air temperature we are dealing with here.
Yeah, well, that actually engages with the next point that I was going to tell you. We have to do something here because we have across the border, we are at the border with Mexico, okay? And in the Mexican side, you will find a very dense cities. For example, Matamoros is a more than 1 million people city, and it's the same size than Brownsville, that has roughly 200,000 people in the same area. So you can calculate the density of people and the urban density, the kind of the type
Right.
of the pollution. Of course, the construction is different. Here the rules are totally different. And when I wanted to have a house built in the typical Latin American style, they told me not. You have to build whatever we build here. Okay, whatever we got. But definitely, I prefer mortar and brick than only wood. But this is most of the things here. Okay, wood is better for heating and the transfer of heat is way better with these materials here. So I think all the things are interesting, and we have to put this into the equation because we have some differences also into the diseases that are affecting people, one side of the border and the other. It would be interesting to have all this information here. So definitely, an invitation to you is open right now. I think Gladys is really interested, and we have to take you here to see the area, the place, and yeah, this will illuminate a lot of pathways. Do you have something to say, Christian? Christian is an architect.
Yes.
Please.
Hi, good afternoon. Nice presentation. And thank you
you.
for that. I have a question related to the configuration of the urbanism. I just want to know if it's possible to do an analysis before just build the space, So it is possible to know, okay, this is a good configuration of urban design or not?
So you could, I mean, I think a lot of the way we do it is to run models. So we run physical models and then change some of the properties of, say, buildings. You know, you can add like green roofs, white roofs, for instance, or you can change the building height or width of the streets, and then run the model and see what happens to, say, temperature, humidity, and all that. That's how we do it. There are uncertainties there as well because the models are not perfect, but it is possible to do. Yeah.
All
Yes,
right.
I was thinking because okay, the downtown they will still growing, you know, so we don't know, okay, how many parts we need to get lower the heat or something like that. And
Yeah,
what happened
it's
with the build materials? Okay, this is a good material for the building or no?
yeah, we can plug those into models. Like we can change, like, say, essentially reflectivity of the materials in terms of sunlight, or like emissivity of the materials. So like wood versus mortar is going to have very different values. We can change like vegetation amount in those streets, and then we can run these models and see like what that does to the. That's what we do a lot. Like we have done that in the past, and uh, we are doing that as well now with like those micro scale models where we can get like meter scale estimates. So we can say, if this was a high rise, multi-story housing instead of a single story housing, how does that affect the radiant temperature around it? So we can do that kind of analysis.
And I think that links very well to what Dalia was implying, that how to bring to the city the information and how to provide the evidence to economists so they can really estimate. So perhaps you may have to invest in this area, but maybe health benefits will mean less cost. So I think I don't know. I have the feeling, Dalia, that we are blind to this, and this is so important for the cities and for our own families. And that's why when I heard TC in LA, I was so excited to learn about this, and I'm happy that even though with this changes in public discourse in the US, that you are still looking at this. It's really very encouraging. Now, yes, I want you to come and visit us, and I think this presentation help us to to understand better. But how can we better prepare for your visit? If we wanted you to come to the valley and help us to diagnose where we are so we can have a valid conversation. I feel like I don't know enough to
Right.
be
I mean,
able to.
I don't know exactly what this visit would entail in terms of like, talking to like I have done like university visits, which is just like I talk to like other faculty and just talk about research and then give a presentation. And sometimes it leads to collaboration, but it's all very academic, right? It's not, doesn't really help the community at all. So I'm assuming this is going to be somewhat different than that.
Yes,
Uh,
definitely. We are academics, but we do collaborative, participatory research. So we are very engaged with the Department of Health and Parks and Recreation, for example. So we are very involved with, have community partners. Actually, NERA is very active in that area. And we, um, we are trying to develop place-based knowledge, perhaps at the level of census tracts on how to improve the quality of life. We are focused on older adults, but also families, because older adults usually do not live in alone. Most of this area, 95% is identify themselves as Hispanics, and this creates cluster of families. So we are trying to working with this, and we work with the city of Brownsville, and we haven't worked with the city of Harlingen, which is where the institute is located, just out of lack of enough manpower to work, but they are very eager to work with us. You know, these cities, these health departments, park and recreation, they look for us. We are a resource for them. So actually, and community-based organizations, librarians. So if I say, you know, let's have a collaborative around how to better prepare, maybe mitigate heat
Mhm.
in Brownsville. What do you think will happen, Dalia? People will go?
I don't know. I feel like I would. I'm very intrigued by the idea of how we can use this to, you know, this information that TC has worked so hard to compile, to find uses for it that would be meaningful. I was just thinking about an article that I read that talked about, you know, the level, I guess I don't know how to call it, you know, the number of cases of Alzheimer's in the valley that seems to be a reflection of not only the poverty, but the ways in which people live and the houses they live in. And then you think about this in terms of the heat indexes and humidity, and they are important variables that we could be looking at.
I think people will be very interested. What do you think, Kendra?
I think it's very interesting. I've been wondering and wanted to ask TC how often he works with like urban planners and people who are working with restructuring communities in regards to, you know, because I am familiar with people here who do a lot of you know, green building, so to speak, you know, with lighting and all that stuff. But I'm
Correct.
wondering how many people, builders and development people, like community development people take, and urban planners take all of this into or know about
So
this even.
yeah, so I have been involved in a couple of work that's relevant to this. Like we did some work with the Nature Conservancy California chapter on some of the work with the public health and afforestation strategies. A lot of that data has been kind of shared with like Cal Fire, and so and I've had like meetings with like some government official in the city of San Jose. uh, I don't think that went. I don't know where it eventually went. The one with Olympia, there was kind of a lot of data that we collected within the city, and then we provided the information, and that is being used by them for like prioritizing their uh, kind of rezoning plans. And then we have another project funded by NASA for the city of Durham in North Carolina, where we have had like community kind of engagement circles where we have talked to the community, tried to understand what they wanted. So at least in one case they shared the information about this rezoning plan for a multifamily housing, and then asked us to look at like the literature on like what this means for like say heat. What we found was not in support of their uh, protest, but we provided all the information that we had, and that would allow them to do more data driven, I don't know, uh, development for their region. So this funding, I don't know what's going to happen with that funding, that NASA funding. It's been only 1 year. We were supposed to do for 2 more years, but given the current uncertainties, it's unsure how much community engagement we will be allowed to do going forward. But I think for a lot of these, it's always useful to know what the community need, because I mean we still live in a very different world, I think, academics,
Yeah,
from what's happening on the ground, especially
right.
when you're talking about a city that's I have never visited. I have been to Texas only once, so
Ah,
it's not even, I don't know much
yeah,
about the issues being faced there.
yeah,
So I think it's always good to know what the issues are from the
right.
people who live in the community.
Yeah, because I can think for those who work like in the low income housing and with housing authority or with some of the developers around here. I mean, we have an organization in town called Community Develop. Well, no, it's called Come Dream, Come Build now, and they do a lot of focusing on on housing and affordable housing. And I would just wonder, from a health perspective, someone who's in health promotion and health and about Alzheimer's now and how the environment can affect a person, how much they are even aware of information like this in regards to when they're building their structures and so forth. So because it would, the health benefits, I would think it could help. So thank you. Thank you. It's very interesting. Thank you.
Thank you.
And I'm wondering, thank you, Kendra. And I'm wondering also, the role of the volumes of water, because we have the Rio Grande separating us from Mexico, which is in some areas it's really big. And we have the Gulf on the other side, and we have a lot of branches of the river called resacas, and I'm wondering about that. And I'm also wondering how is SpaceX is going to affect us. I mean, my house shakes every time there is a launch. So I don't know if how these unusual crossings in the space, given the magnitude of these rockets, are going to affect temperatures.
Yeah, I have no idea.
Well, we have to schedule you. We have to schedule you for a date with a launch. It happens
It's a
once
very
a month.
unique
Once or
environment. Yeah.
oh yeah, that's
So
one month.
we'll take you there, and so yeah, I think that the next step for us will be, I definitely want to go over the resources that you provided to be able to have a kind of a deeper conversation with you. And also, I think that we are going to talk to our partners to see what they are interested, if they would like to join us in a conversation about this. And yeah, I think, Kendra, that was a very good point about housing officials. They are so nice. You're going to be surprised how open and eager the people, even public health, even public officials are about, collaborating. And this is a new university. There was no university in the area before. There were, but not in the health, not a school of medicine. And I think that that's one of the reasons why these organizations are enthusiastic about collaborating with us, and they have a lot of hope. We feel the weight of responsibility, in providing actionable points for public health officials and for the community organizations. I do, I interact a lot every week with them, and even the older adults that visit us, they pose all kind of questions because they see us as a resource, trustful resource. So we're not trying to sell them anything, solar panels, which you didn't mention, but we get bombarded by these solar panels and stuff like that. And so it's been really a pleasure to have you with us. I think that we just need to put a date. I think perhaps if you're available in August, that will be a good time.
It's going to be scorching. It's going to be
Oh.
scorching. You
That's
will
fine.
feel the heat.
Yeah, let's discuss that offline. Yeah.
Yeah, or
Right.
July, or it will be the best for us, I think. And so to give us some time to prepare our partners and make a program and read and learn. And I think also the demographers, we need to and sociologists, I think, will be the disaster program will be good. But the whole point is to help us to design strategies to study our region. How can we best study our region, and how can we So initially, we need to study to be able to provide any feedback. And we, and in terms of health, association with health, survival, and general mortality, for example, I think this is a critical issue given the number of deaths that occur in the summer every year, and strokes and things like that. We later see the Alzheimer's, but first we see the stroke. And so that's something that we would like to plan how to propose a study that we can really give us some actions. And we start also because our methods are participatory. So we always start with dialogues, not only with experts, but with community members. So we start and the public health officials, so we can, not only develop knowledge, but the actionable knowledge, we call it. So thank you so much. Really, it's been a pleasure. So let's keep the conversation about you coming to visit, and thank you for accepting our invitation to this webinar and to our visit. Thank you so much.
Thank you. This was a great conversation, and thanks for attending. Yeah.
Thank you, Neida. You tell us what you have there.
Okay, we have new interns with us. These are their faces. And Andrea has been with us for a while, but this is an internship during the summer that we have here. These are our new interns in Caroline, Christine, Kennedy, and Shanna. We also have announcement for the next session. Sorry, this is in June 17. I think it was today. Anyhow, we have the upcoming Alzheimer's Association International Conference on July 27 to the 31st. We will have some presentation from our groups and other supporting groups from us. And
and I have to say that the virtual attendance to the Alzheimer's Association, it's going to be free.
Yeah.
So this is a tremendous opportunity because it used to cost like $700.
Yeah.
So, Neida, what's the next Brain Up? When is the next Brain and Beyond? You are muted.
Yeah, it's July 1st.
July 1st, and it's going to be
July
these people?
1st. Yes, and it's going to be Dr. William Dow, and he's going to be bringing his PhD student, Chris Soria, if all works out, and they're going to be presenting on the Hispanic migrant cognitive aging.
Sounds very interesting. So thank you very much. Thank you all. Welcome to our interns. We are so excited that they are with us this summer, and we look forward. I think we still are waiting for paperwork for one or two more that I've seen in the administrative paperwork, but we are very excited to have these strong students, undergraduate and graduate students with us. So thank you so much, and see you in 2 weeks.
Thank you.
Thank you.